Okay, so my topic is Scratch to other languages. So if you've had your kids using Scratch, you've explored Scratch, and you eventually want to teach it. So this is a very CS context, in the sense that obviously Scratch can be used for making in general, as can these other tools, but I'm coming in from a CS bent, like a computer science bent. So I picked sort of a series of lessons that we developed at our school to do the initial transition for kids. And I'm going to discuss those series of lessons, sort of why we structured them that way, the learning objectives around them. I'm not going to teach, it's like 7 lessons, so I cannot teach 7 lessons in 45 minutes. So that's a big takeaway, it's 7 lessons, it's not one magical lesson. And we'll sort of talk, I'll leave time for questions and answers at the end, your thoughts, if you're like, hey, you could have done this instead, I did this and it worked a lot better, like, dear God, tell me, because I would love to know. I'm also learning here. So, I'm going to address some concerns that people sometimes ask, like, why start with Scratch at all? Like, this community, I don't really feel like I need to sell this as hard, but there are people who advocate, you don't really need Scratch, you can start with other languages first, like, why make it harder to transition for kids? Just start them on the thing that maybe you'll do more development in. And so there's other reasons, but the 3 ones that I could point out are syntax errors. So if you're using a block-based language, it's kind of impossible to write a syntactically incorrect program. I know in Scratch there's certain things that will drag and drop technically into the wrong space, but like for the most part, Scratch handles syntax for you very nicely. And at least as a teacher, in my experience, why I like coming at it where syntax is not the problem is I get to focus on kids' ideas in terms of sequence of instructions, what is the order they're following, what is the logical representation of this concept you would like to make in sort of the computer science framework. And it's not, hey, you forgot parentheses, hey, you forgot a semicolon, oh my God, you hit return when you shouldn't have. And so it lets me initially ignore that to focus on the ideas. Sharing and hosting, so I picked Python as an arbitrary language. This is true of a lot of them. Scratch.mit.edu, if you've written a project, you hit publish and voila, you have shared your project with every person ever. And if they have a web browser, they can see it and you can get feedback. People can remix your projects. Python, I've heard people say GitHub does that, and I'm like, great, teach GitHub to 9th graders. So there is stuff here, right? There's very rich sharing environments, but the conceptual framework, then technical leap, students need to do that. I think it's a little unfair once their first experience to be like, all right, GitHub, here's 12 commands to get your repository set up, and you don't really have a conceptual understanding of what it's doing. And then the other reason that I've articulated that I really like it, and this is sort of block-based languages in general, it's like self-documenting. So the palette of instructions in Scratch, right, the blocks that you can pull out, that is the documentation, more or less. Like, here's all the commands you can use. Whereas if you want to teach kids another language or some game development framework, or in this case I just chose Turtle Graphics, kids do need to read through documentation and know how to read through documentation. If not always, but you can parse down the documentation, you can give them cheat sheets, but what you're going to have to do is teach kids to read documentation. High-performing kids will just sort of pick this up, but I teach in an unscreened public school in New York. A lot of kids are not just going to magically pick up documentation reading. That's like a taught skill. And I'm working right now with juniors of how do you scaffold up reading documentation.
Juniors in high school?
Yes. I majored in CS in college. I didn't find this super challenging, but the biggest thing I've learned in teaching is they are not me and I am not them. And if you really think about documentation-wise, all the things you have to read and understand, and more importantly, all the things that you need to ignore, right? Oh, I don't need that, I don't need that, I don't need that. That's a skill to say I can safely ignore things.
So they have trouble searching through the documentation and finding what they want.
Yes, I've even seen kids where they find what looks like an answer and they just copy and paste it in and they're like, it doesn't work. It's like, well, that was an example of the concept. You need to understand the kids, I think most kids can learn that, but in the same way that I couldn't just say hey, solve algebra equations without teaching it, modeling it, and a lot of the other things. I think for a lot of kids, this is a barrier if you're unwilling to explicitly teach it. So Scratch is nicely what I'll call self-documenting. So that's why I start with Scratch, and I think it's good if you've never been exposed to those. And then why leave Scratch? Right? Like why do you even need to leave it?
Are you sharing this? You're sharing this?
I'm sorry?
Are you going to share this?
So he is recording it?
No, are you sharing the exact presentation?
I can at the end, and it's not shared at this very moment.
Okay.
But I will write at the end and send you a link. And this is, I've had people debate these goals. If you don't share these goals, then maybe you don't leave Scratch. But my goals are to reinforce core CS abstractions via multiple representations. The idea is a loop is about a single sequence being repeated, not the repeat block itself, not for loops. I mean, technically recursion is looping. And so the more representations of a concept you can provide kids, the hope is they will start to see it as the abstraction, not as, oh, the Scratch tool. So there's other CS abstractions, and again, I'm coming at it from a CS angle, that are not easily represented in Scratch. So functions, like Scratch is Turing complete. I don't know if that means anything to you. You could make functions happen if you really wanted to implement them, but no way would that be appropriate, I think, for a lot of kids. There's other things around like lists. So like Scratch does not run the gamut of core CS concepts. And so if you want to get kids to certain concepts, Scratch does not allow them to be easily represented. And I found that when you transition to another language, so in this example, I'll be doing Python. I have a lot of kids who are like, I already know how to program. And what they're really saying to me is, I know how to copy and paste some code from the internet that someone showed me once. It's true, right? And I'll be like, all right, like write hello world. And they'll be like, what do you mean? I'm like, well, just write hello world, like if you know that language. So I find that showing like, here's Scratch, here's this other language, we're solving a very similar problem in both, like look at the similarities, gives me leverage to use Scratch because I'm making the case that they are fundamentally equivalent. Like I know that, but I don't think the kids always know that. Okay, so.
Do you show them the equivalents right next to each other?
Yeah, I have slides and lessons. So this is like a series of lessons.
Right.
And so yeah, what I've done is I have a slide where it's the Scratch code and it just fades out and the Python code fades in and it like looks exactly the same. So I'm like, all that's different is it's not blocks. Like I keep the message I tell kids is, like if you love typing, I guess it's different, but other than the typing, it's the same.
So you really do side by side.
So I'm gonna tweak this. My initial was variables. But I realized to explain it in 45 minutes with the variables part being rolled in, so I'm going to tweak this presentation a little bit. So we do it the way we did it and this is not the only way, but this is one approach. So I do want to emphasize, like this is one approach. This is not the only. We do Scratch to Python and we do it via the avenue of drawing. So in Scratch, there's the pen commands. Right, you can put a pen down, you can move the character all around, and you can make drawings in Scratch. There's a lot of assignments you can do with drawings with various degrees of difficulty. You can incorporate a lot of core concepts. And the nice thing that all Python, that's covered up, that all Python libraries sort of come with for free is Turtle Graphics. And Turtle Graphics, so thumbs up, I know what Turtle Graphics means. Thumbs down, could you just elaborate very briefly on what Turtle Graphics means? Okay, so Turtle Graphics is just when you they call this a turtle. This is from Logo, from way back when it was literally a turtle. And you can tell this thing to move a certain distance, turn left, turn right, and it leaves a nice pen trail behind. So it's a lot of people's introduction to CS from back before Scratch. And you'll notice in both of these, I work at the Academy for Software Engineering, so they do a project, right, AFSE. That's an AFSE, sort of scaled weirdly. So like they're similar projects. So I'm going to go over the scope, and so there's a lot of lessons here, and that's the first thing that jumps out at me, is that what I'm about to show you, and I'll go over these individually, this is 7 lessons, and this also ignores some other things we did, but like if I had to isolate the lessons that allowed me to transition, it would be these 7. And the periods that I taught these in were about 60 minutes, so 7 times, that's about 7 hours. So like the first big takeaway, which we can go to the end, is it's not some magical, here's the one project that if you just throw them at it, they should be able to do and everything will be perfect. That's my experience. So like I'm gonna go over sort of the learning goals of each, my thought process, and then a brief summary of what they did. And if you have questions along the way, concerns, comments, do let me know. So the first lesson in Scratch that is relevant towards stuff like that, and I learned this sort of the hard way by trying and then having to go back. Given a set of Scratch-like drawing instructions on paper, trace the instructions line by line to make a drawing. So if I gave you instructions on paper for drawing in Scratch, which are like move, right, and you can point in the various directions, can a kid trace that on paper to make said drawing? And what we have found, and I have another teacher teaching this curriculum now, I don't teach this year, he was like, why are you having to do that? That's silly, right? Like a lot of kids don't intrinsically do that. Like given a set of instructions, they don't follow it line by line. They try and absorb the whole thing and produce some drawing that is typically incorrect. So I'm gonna skip ahead here. So like this, as boring as this is an example exercise. Like given that start, and I don't just give this to them cold, we talk about it a little bit. Could you trace the dots to produce a drawing for which I have the answer or for which your peers have the answer? The biggest thing here that kids struggle to do, and I'm not quite sure why, I think it's because they've been taught in a lot of their lives to like summarize and to abstract. In English class, you get taught, words, sentences, paragraphs. There's all this summary. Kids really, not all kids, a lot of kids struggle to like turn off the summarizing part of their brain and just go, all right, go down 4. All right, go right 3. Go up 2, and just ignore the whole problem and focus in on a line-by-line sequence of instructions. And if you want to tie this sort of to bigger CS concepts, this is the ability to trace code, like using a pencil and paper to trace out a sequence of instructions. This is a fundamental skill to kids debugging broken programs. I've seen kids like try to write programs. I'm like, all right, let's trace what's happening here so we can have a good idea of where the problem is. And if they struggle to do it, it's hard for me as a teacher to even go about fixing it without just telling them, here's the line of code to fix with no deeper understanding of why. Any questions on this?
Can I just ask you, so you're saying that you're using this towards the end of when so they already are exposed to Scratch and you're about to transition into another language?
You could start teaching Scratch. This is like pre-Scratch, right? We go over like down means go down, right? And the other things that I'm gonna call out that are subtle, but it took me a while to learn these. The directions are absolute. Down is their down.
Right.
It is not the turtle's down.
Right.
Right? Right is their right, up is their up. These are like, you could use north, south, east, and west if you wanted to. Relative directions kids need to be taught.
Yeah, I was gonna say, like when they do the code.org platform, the hardest thing is, no, you're facing the direction of the Angry Bird. So
Yes.
what's his left? And then like.
And the thing we'll come back to this paperwork. I've done the relative directions. The nice thing about paper is you can rotate the paper so that you face the same direction as the turtle, and you get the sense that like, oh, it is not my directions, it is the turtle's. And again, this is for 9th graders for us, like kids struggle to get my direction versus the turtle's direction. So we start with that. Lesson 1, sorry, I start counting from 0 because I'm a computer scientist. So once we have confirmed that kids can do that consistently for some series of instructions, we go the other way, given some sort of drawing. Right, so the first way is here's an arbitrary set of instructions. Usually you want to make it a nice picture so they like feel rewarded when they get it. Write Scratch-like instructions on paper that would produce the drawing. The on paper part, I'm kind of addicted to making kids do work on paper first before I let them go on the computer, because that allows me to troubleshoot misunderstandings. Like I've seen kids copy from neighbors or sort of hack something together with no framework for understanding. And the goal is not that they get this thing perfect, right? Perfect is crazy, but I can see they have a framework for tackling the problem. And then once they have like some paper sketch of what they want to do, translate that into a Scratch program. So in this case, this would be, oh, you guys can't even see that really, can you? Can anyone see over there?
Mm-hmm.
This, it's like,
The K.
this is like K, D. So this is Kobe's. And so this is his program he used to produce that. But again, prior to that, the assignment was, draw your initials in Scratch. And so what I let them do on paper is like draw the letters that they want to draw. I teach them block shaped because that you can use point up, point down, point left, point right. And then after, right, they get a peer assessment on that, like, oh, that mostly looks pretty good, or me assessing it, then it's like, okay, go on the computer now, try and hack it together. And so the working with Scratch becomes much more about the debugging skills and the like self-assessment skills and the testing skills and the fluency with the tool, and less about I need to design a program in my head with no prior work and implement it in Scratch. Because if you start to think about the cognitive load students need to do that, it's a lot. So.
Do you do any pseudocode with them since they're doing this? It seems like you wouldn't necessarily bother with that.
So
Scratch.
you could argue this is pseudocode. I need to read the research paper. There's some research that generic pseudocode, like this corresponds very tightly to Scratch.
Yes.
Like it's pseudocode with an extremely, like it's like a 1-to-1 correlation. Higher level pseudocode, and I wish I knew why, but I can try and find the paper for you, actually doesn't work very well. Like kids do worse when they're given pseudocode solutions in classroom settings. I can try and find that.
When they're given, or when they write them themselves?
The act of pseudocoding is mentally very hard. And I have like my intuitive explanation of why, but I want to read the paper and not just regurgitate like my preconceived.
I was just curious because I used to give that for homework all the time.
Yeah, so I was surprised too, because that's when people taught me like, here's how you teach this lesson, they're like pseudocode it first, and like apparently that is not a great strategy per some research paper that I will find for you.
Okay, that's good.
No, it's not obvious, right?
Yeah.
So they create their initials in Scratch, so that is they get to pick, or they could pick other initials, I don't really care. They draw some letter of their choosing, they outline the instructions, like they produce the instructions on paper with some peer checking, and then it's like, okay, go into Scratch and make that. So after we've done that, that's pretty much basic drawing in Scratch for everything you'd want to draw with right angles, right? More or less. Like you drop the pen, you can turn, you can move, etc. So when we transition into Python, and what you'll notice there's a lot more lessons here. This is because of the things I talked about, that Scratch, no syntax errors, and documentation and various other things. Like, so Python is going to be a higher cognitive load, so there's certain things we need to teach them. The first lesson in Python that I found, this is a syntax lesson. So given a Python terminal program, so I give them a program. Not that they, like, it is a picture of a program on the computer, so they have to type it themselves, or it's on a piece of paper. Predict the drawing that will result. So this is purely to get them used to the syntax of Python and seeing lots of example programs, like lots and lots of example programs. This is purely intuition. I'd love to see if there is research on this. I feel like we often expect kids to write lots of programs without ever having seen programs. And like in the same way that I feel like English would be hard if you didn't read books before you started writing stories. I have some intuition that like kids need to see a lot of programs before they're asked to produce. So the goal there is for them to be tracing again, like given a Python program, try and trace and predict it. And then on the computer, test it out. So I have this Google form, which I'll show you here. Which is, I give them this, that's a screenshot, right? I don't really explain to them what import turtle means, I don't explain this other stuff, very briefly, and I say, on your paper, what would it draw? Please record for me, like, what it draws on the screen, and then why do you think it will draw that letter? Like, just, to measure that they're tracing, and then immediately after the prediction, they're allowed to type in whatever the program was, run it, and then see. So this provides this, like, self-check of, did what I predict match the outcome of the code? One of the biggest things I've found with kids that like I only surface after about 6 months or a year of teaching is they won't even know what a program's supposed to do. So like their ability to evaluate that they have a problem, right? Like if you don't know what it's supposed to do to begin with, knowing you have a problem is impossible. And so getting this idea of for small sets of code that you've seen, try to predict what will happen in that code. And is your prediction accurate? And if not, why not? So again, this is to develop tracing skills, debugging skills. Lesson 3.
Can I just ask when they're predicting what the code outcome is, do they have to, they don't have to write any explanation why they think it's gonna, like, at what point do you explain to them like a computer's really stupid, it will only do exactly what you say it to do. It sounds like a lot of this is getting them to like really understand the fact that computers only.
Yes. I found that's one of the biggest weaknesses is kids try to summarize code for like when they have a project in mind, they'll be like, oh, this is, they won't think it's close, they'll think it's right because they thought when they were writing it, that's what it should do. So it should do that. When it doesn't work, there's this complete breakdown of like, oh, the computer's only doing exactly what it's told. What are strategies I can use to get myself out of that? Because when my goal eventually is not to have kids tracing just little bits of code, it's to build things.
Right.
But if they don't have that skill of like, let me stop, trace, debug, test, it's hard to get meaningful large projects that are just me telling them, write this line of code, write this line of code, write this line of code, where it's sort of an independent problem solving process.
Right. And so when you transition to Python, how far have they gotten in Scratch in terms of like, have they used variables, loops?
So,
like, do
yeah.
they really understand Scratch in a really complex way, or have they used Scratch to do like animations and little like animated
No, so
drones?
this is my aim. This curriculum that I developed for Scratch, I was my first year teaching.
Okay.
And so like, my goal was, the one thing I want to suss out is like, what does it mean to really understand variables? Like that's real deep if you want to go real deep with it. So it's for a context, can they variables theoretically can be used as just constants, right? Where you
Right.
stick a number in there and it is forever that number, and all the kid really needs to understand is every time you see this name, replace it with the number. Which some kids don't get. Like when you say, have the cat say the variable name, they think the variable name is gonna come out, not the content of the variable.
Right.
And then that's separate from like, oh, a variable can change in sequence, right? So like I could change it lower and down here it's gonna be 5, but up here it's gonna be 3 because I change it, which is different from pulling a variable out, adding some number to it, and then sticking it back in, which is like a change by, and like, sorry, it just took me 6 sentences to explain all those things, and I feel like that's, if you want kids to get CS, you need to be like, oh, do you understand this versus that? Because if they don't understand those in that level of detail, like making a video game where the points get updated, like I can show you how to do it, but do you really get it?
That's like I spent a lot of time teaching kids variables over very long periods of time.
Yeah.
Months.
Yeah, absolutely.
So that's we went through all of that, but it, like you said, it was months.
Yeah,
Like,
it's
it was
not, and it's because it's not easy to get it. And then,
Right.
Especially I deal with 9th graders learning algebra, distinguishing between, variables in algebra, which are equal versus no, this is not. It's like a box that you can put things in, so. Anyway, so we do that with Python, and then we have another brief lesson. And this is one of those things that I would have never thought to teach unless I had experience with the kids. Given that, the thing on the bottom, what line of code is wrong? Given this thing, what line of code
You're gonna
is
say
broken?
line 5 and there's not 5 lines.
So yeah, that's one. There's not 5 lines, right? Like there aren't. I know there's truly 5 lines, right? So like you can say like 1, 2, 3, 4. It's like, but there aren't 5 lines. And so the answer, I don't know.
You could scroll. That's not necessarily the whole.
In this case, I say this is the whole program.
Oh,
It's just an
okay.
exercise.
So is the error that there's only one argument given instead of 2? For
Yeah, and that's also confusing. I haven't talked to you about arguments, what that formal term means, but so again, if kids are expected, the point here being if kids are expected to write syntactically correct code in a typed language, this is going to happen to them all the time. And you need to know they know how to parse this in some way, right? They don't have to know arguments, they don't need to know type error or file, what is a strategy you can teach them to say, hey, when this happens, here's where you should look for a fix. So we talk about lines are not necessarily lines you see. Lines are, this one or this one or this one or this one. So line 5 is 1, 2, 3, 4, 5, right here. And then I don't get into a formal discussion of arguments, but it says, something's wrong there. And they have a reference sheet that write. In this case, this function takes an amount of degrees for turning. And so it's missing that. And literally just exercises and lessons with the kids on when you get an error message, how do you read an error message? because that's one of those skills that I remember never being taught that. And if you get it, you can move on. If you don't, this becomes this impossible task to like guess your way through.
How many lessons do you spend on this? Because this is where when they start pushing back on I want to do real programming, we do one lesson like this, and then they run safely back to the world of Scratch and say, you're right, we'll just stay in Scratch for a while. So how many lessons?
This one, and this is the other thing, I do it one, but it's extremely limited in scope. So like I'm not teaching them all error messages, because that's impossible to do in one lesson. I'm teaching them the ones they are very likely to encounter with turtle graphics for the types of projects they're going to do.
Okay, so in context, right?
And the biggest takeaway is like, just like honestly, if all they learn is look for this thing and count down to that, and I give them examples where there's an error the line above, because that, compilers aren't perfect or interpreters aren't perfect. Like sometimes they'll say line 5 is the problem, but really line 4 is the problem. So just this strategy of using this to hone in on a line to examine, and then if we've reasonably taught them to trace, we'll get to that later, which is like a semantic problem.
The right part, like in module right. So, like if they finish the line 5, then they know it's in the right.
Yes.
They can
So
go back to.
This is another clue that they're going to the right line and like calling that out explicitly. And you can start giving kids like complex, like the nice, with all of this stuff, I'm not talking at all about differentiation, like low level exercise versus high level exercises. Like a low level would just tell me what line it's on. A medium level would be there'd be multiple lines and like tell me the fix. And then the high level could be like, there are semantic and syntactic errors, like using these, try and fix them as best you can. So I'm just going with like the core concept. So they need to be able to identify errors. So they can't identify errors in turtle graphics, they're totally screwed. Like there's nothing they're gonna be able to do. And I teach like classrooms of like 32 kids, sometimes like 50, what's the legal limit on IEPs in a room? 10, 12? 12, yeah, so like sometimes those classes will be ICT, does this mean anything to anyone? ICT classes? Yeah, so CS does not get 2 teachers in that class. So like this is not something where I have the bandwidth to individually address,
Even though that's like illegal.
No, it's required for core like academic classes. This is an elective class.
This is not considered a core academic class,
Yes.
even though you're at the academy and stuff.
Well, this is DOE structures and teacher time. I do not blame my school for this.
Yeah.
But the reality is, I can't individually work with kids to say, oh, tweak that. Like there's not, like if you do the math, there's 30 of them, there's 1 of me, there's 60 minutes, they each get 2 minutes with me, assuming I never talk in front of the room. Like this needs to be taught in a group way and measured. And when I see kids who can't do this, those are the kids you pull in for tutoring and say, okay, you really need to get this. Question?
With those students who aren't good readers, like I have a lot of students who, like same thing, some students who are high level, medium, but I have a huge chunk of students who aren't avid readers, and like reading that might scare them.
Right. So I don't put this up and say like figure it out. We talk about like what are the things to ignore?
Yeah.
And like what you can start, and again, like I would honestly, this is where you start talking to like ESL teachers, you start talking to English teachers, like because in a lot of texts there is a skill of having to ignore certain things. Like looking up definitions in the dictionary, you need to know what to ignore. And I'm not as good as I'd like to be, but like we talk about like focus in on this, do these match. And the nice-ish thing about turtle graphics is there isn't this infinite set of correct commands. It's pretty scoped. But this could probably use work on that. I agree. It's like that's one of the challenges too.
I would probably give this to them on paper and have them highlight.
Oh yeah, these are all initially, everything I do initially usually is on paper because it forces like a thought process, not a copy paste from my neighbor process.
For the students who are low-level readers, especially, would it be beneficial if there are specific things that are errors that usually happen, common errors, like to have like a little cheat sheet saying this equals this or this
I go into fixing these things, and I did provide that for some of them. Right now I'm going through like the lowest level, like the bare minimum every kid needs. Because most kids, once they a good chunk of my kids, once they can identify this, and we talk briefly about fixing it, can sort of identify. And then those kids, yeah, you can provide cheat sheets for common fixes. You get to focus more of your time because you know the rest of these kids are proficient. But this right now is just like, I guess I'm calling this out because these are things that people skip over when they teach. Like, can you just identify an error? Like, given compiler or interpreter feedback? Like, I don't remember being taught that. I don't see a lot of curriculums where they say, like, here's a lesson on just and only that. And these are things that I feel like, again, if kids can't do, they'll feel like they can't do CS, even though it's not really their fault.
I feel like you're desensitizing them a bit to being afraid of it and running back to scratch, as you mentioned. And that you're also teaching them that this, although it looks scary, is useful if we can just make,
make some
find
sense
out what it is.
Yeah.
So that even if they don't understand it completely, they get this message and say, okay, I'm supposed to be able to do something with this. Now I can form a question, ask my neighbor, or ask my teacher.
Yes, and that's where, like, if all I get them to form is like a refined question, I want to turn all their "it's broke, it doesn't work" to "it's broken here." Because, like, it's broken here is something your neighbor can help you with. It's something I can quickly help you with. If all I ever did was turn kids into people who say my program doesn't work to my program doesn't work here, like, I feel like I was massively successful.
Yeah, absolutely. It's nice that you've broken that down. It's a very clear skill they must go through.
Yeah, and and I know people have, especially in this community, there's different feelings about testing, but like, I test this. Like, they get little quizzes that are like, hey, use this, just circle the line. So they're not meant to be super challenging, but just as a quick check for understanding. So lesson 4, this is where I get to teach geometry because I realized I was teaching kids who only had algebra, and even in algebra, they're not the best. And actually, like, a weird way of teaching geometry. So what we do for turtle graphics, there's no absolute directions. They're all relative, right? It's like the turtle's right, the turtle's left. It's all in degrees. And so what we try and teach them is numeracy, not measuring an angle with a protractor, which weirdly a lot of them, but like guesstimating angles. And not every angle under the sun, but pretty much 90, 45.
60.
60 I guess we might go into that.
So does the triangle.
That's true. But we haven't, like, for these drawings, a lot of them are all 90-degree turns and 45s. So, like, we literally have a lesson where it's like, is that more than, less than, or exactly 90? And we teach them the strategy of, for a drawing, you can draw this imaginary right angle, and then you say, is it to the right of it? Is it to the left of it? Also, this idea that the angle the turtle's going to care about is not this angle, it is this angle, is also something that is not intuitive, especially in algebra when it's always the interior angle. And you'll notice, like, these questions, so this is a more example of some differentiation. These are multiple choice. And then we sort of transition to this.
Do you put the turtle on there? Like, do you have a turtle?
So when I'm teaching this I have PowerPoints, and I'll show you next. These will be like 90-slide PowerPoints. Not PowerPoints, Google Slides, because they don't have nice animation features in Google Slides, unfortunately.
They do.
Do they? Yeah. Not for, like, drawing arbitrary paths. Or if they do, tell me, because you'll just save me a bunch of work. So just take that thought. So, like, yeah, I'll either use a smartboard and I'll draw the turtle. I'm like, okay, this turtle starts here. It ends up here. So, like, the picture they'll see in class is sort of animated. But what we want them to get is this idea of, if they make some arbitrary drawing where it ends like that, like, how do I go over it? So we go from this, and then we provide them a scaffolding code, right? And, like, this one, we literally tell them it's a 45-degree turn. Can you just plug in the 45, right? So there's, like, a nice pattern match there. So this is if I'm helping a kid and helping them with the angles, because that's where they struggle, they at least know that given an angle, they should be plugging it in there. This one, right, there's no indication, but the idea is that they could guesstimate that it's 90. The goal is not that they get the perfect angle, but that it's a sensible-ish angle. Like, this is what, to draw internal graphics, you need to be able to, like, guess at angles in a reasonable way. And then what we sort of do as a class towards the end, right, these get a little bit more complicated, right? And then finally at the end, and we work through this with them, where we sort of do about half of this, and then I let them go on the other half, check in and see how they're doing. It's like, they don't have to think about the sequence of code. All they're thinking about is, like, what is the turning angle for each one, what is the distance, and they fill it in. And this is on paper. Does that make sense? And the goal here is, do they have numeracy with angles? Because if they don't have numeracy with angles, again, drawing internal graphics is impossible.
That's something I've been trying to work with my students on is, are you having a math problem or a coding problem? and trying to get them to realize which the problem is so that they can ask the right question.
Yeah, so one of the things, and if there's different, I am really, and I'm from a software engineering background, like, you know, you see whiteboards in Google and like all your interviews are just here's a whiteboard, sketch out the ideas. And so I'm very, again, not that their sketching of ideas is the solution to the problem, because that's boring and rote, but to try and separate, do you misunderstand the concept from does your code that you translated the concepts into have a mistake? I'm really trying to like separate that for them. And this is one of the ways. All right, so then we've identified turns and angles via like, and you can do a zillion exercises like these scaled arbitrarily to arbitrary depth, right? You can give challenging problems to kids who are higher skilled, less challenging to lower skilled. All right, we're almost there for drawing internal graphics like a real picture. Okay, so after we've done, hey, you have some numeracy with angles, if I gave you some picture, right, because this is ultimately what I want the kids to do, is like draw stuff, internal graphics, like something you think would be cool. If I gave you a picture, could you, and again, not perfectly, sketch out a solution in code on paper without the computer? So that when you are using the computer, it's a matter of tiny debugging, tiny fixes, but you have a good conceptual framework. So this is literally what happens in class, where we talk through, and this is like Q&A, I let them do it in groups when we come back. Right, and I give them the sheet, sorry, this thing looks insane up here. I give them a sheet with a turtle that has like the left versus the right, and so when they're tracing over it, they can like hold it up to their screen, like turn the paper. So again, it makes the relativeness of the turtles like, left is not your left, it is the turtle's left. And so like the other thing that I'm not talking about right now, like when you make these drawings, like when a kid draws something on paper, like the size of this is like whatever the heck you want it to be, right? Like this edge could be 100 or 50. What matters is proportionality. And so we like talk about that like you need to assign numbers to these. And then that actually provides, if you want to get into variables and why they can be useful, you can start making these scaled drawings that like automatically scale nicely. So we go through that. So you can see like this is the animation to give them the idea. And then they finally get to do this. I call the assignment a game of turtles. And they're supposed to draw, this is where it's more freeform, like I think it fits more with the project-based stuff, like draw a castle. Any castle, anything can be in your castle, I don't care what. There's certain minimum requirements they have to do, like it has to have some outline that is castle-y shaped. But after that, the more creative they get, the better they do. And so like that is something a kid drew in my class using turtle graphics. And you'll notice there's like colors in there. So I do give them reference sheets for things I don't teach for the kids who are more motivated, right? Like so this kid figured out colors and how to fill things in. But the bare minimum here was like, to do a castle, you need, like, I strongly believe all the things that we went through were kind of necessary. If you didn't know how to do any of those, this project is impossible.
So, at what point do you put in a repeat to do a square? Like, do you ever do basic shapes before you do a castle?
So,
like,
we did in
repeat
Scratch.
forward.
We did in Scratch, and because this.
Okay, they
So
did
this
do
is
it in
the
Scratch. Okay.
the differentiation is not cool anymore. It's multiple entry points. Is that the term now?
Whatever.
Whatever it is.
Yeah.
So we did loops in Scratch to make various like regular geometric figures or like stars, and then make a sky full of stars and stuff.
Okay.
So we're going back to Python. Nowhere do I talk about loops, nowhere do whatever, but some kids will be like, wait, can I just use a loop? And I'm like, yeah, you can. And like on the assignment page, there's like Google for it, and like they click and it doesn't let me Google that for you. So it's letting them try to extend, make the connection, and then I can hone in on those kids for making the connection, whereas the kids who struggle more with like turning angles and movement, like, so yeah, we've covered conditionals, loops, variables in Scratch, and we're going into Python without bringing all that in, because bringing all that in, I feel like the cognitive load is very high.
Right. But they did, okay, so they really did get far in Scratch, like they went through.
Kids got, yes, we exposed them to things very far. It depends on the kid how much they got out of that. And this is sort of the spiraling, right? Where it's like if a kid maybe struggled with tracing in Scratch, this is another opportunity where you're trying to reinforce those skills, but give them a little more freedom.
And this kid clearly didn't struggle in Scratch, so
No.
he understood it and like.
The thing, I wish I had it, it's probably my email somewhere. We actually had a girl Like my metric where I felt like this was a good one to go over is like we had a girl who very much struggled in math. Like division sign was not quite familiar with it. Like just the line with 2 dots, and like. And not that she did a great castle, but we saw her get out a whiteboard and start like sketching out the thing with like the turning angles and doing what we did, which made I didn't teach her, it was another guy who was in her class, but like made us discussing how you go about this like feasible in a classroom of 30. Whereas if she had not been engaging in that, it's like, I can't teach you on the screen the concepts and the code. So we got to sort of hone in on the code. So I think this one was successful for our first pass at it. My takeaways, these were the big things that I think I would do for any scratch to something else. Use a problem or context is very similar in both languages to allow for reinforcement, transfer, and abstraction. So reinforcement in the sense of, hey, maybe you weren't as good at tracing as we would have liked. Here's another opportunity to do it as a low-level skill. Transfer, the idea that doing this in Scratch is the same as doing this in Python, would probably be the same as doing this in Java, would probably be the same as whatever. And then abstraction, the idea that we can trace Scratch code, we can trace Python code, that the tracing is, like, that's just one example. Try to explicitly, and we spend a lot of time brainstorming, like, what do we actually need to teach kids? What do they come in with? Teach the skills necessary for the new environment. Not all students will make the leap that the new language requires. So in Python, it's how do you read error messages. Scratch, you can make all these drawings with absolute directions. You need to teach relative directions so that you can be sure it's a fair ask of the kids in an assignment. And then the last big one, oh yeah, sorry, new language requires explicitly teaching development strategies. I didn't mention this in the talk, so I've seen kids where they write 50 lines of code and then hope it works, and like that's insanity town. Like a few lines, check if it works. A few lines, check if that works. A few lines, check, like, that's not obvious. If you think of how you write an English paper, how you solve a math problem, you just write it out.
Yeah.
And so develop offline. For me, that's paper. It could be whiteboard strategies for students to debug code. So for this, it's tracing. It's if you're given an error message, can you identify the line? And that activity of saying, let's find the error message is like, you're telling them, no, this will never be right the first time, ever, 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 ever. Like any interesting program will never be right the first time. Because they're not, I mean, especially for a lot of kids who are used to failing, like that's just another like, oh, I failed, I can't do it, this problem is impossible, I'm done. And it's like, no, that everyone fails the first program. And that's normal. So those are my takeaways from doing this and things that might have transfer. What time is it actually? 11:48. So I guess we have like six.
What's
six,
the
7.
difference between, what's the semantical, like the syntax errors I know, but where are the semantical errors?
The semantic, so
Yeah.
that's where we teach angles and tracing, where kids will turn right when they should have turned left, or they'll poorly estimate an angle. The whole drawing gets thrown off.
That's the math, okay.
Yeah,
But
and I mean, you could call it, I guess it's math. Yeah, it's math.
that's the math errors as opposed to the,
Yeah, or the sequence is off, where they'll like skip drawing a line, and so the whole castle will be messed up.
okay.
And so this gives me, when I'm going around when they're doing these assignments on the computer, right, they're all sort of independently working or talking to neighbors, I can provide these quick troubleshooting pointers that it's like, they're like, this isn't working. I'm like, all right, like what line of code did it stop work? Like if it's a semantic error, right, the castle looks great up until, you know, you get the first column right, and then it goes crazy.
Mm-hmm.
Like what line of code does it start to not work? And when I ask them that, it's not something they're like, what do you mean? It's like, no, we did this on paper. Tell me when the drawing you're making by hand is like looking weird if you just blindly follow the instructions. And so they can do that, then when I circle back, if they have it, they're like, oh, I think it's here, and I'm like, yes, that is there, like, what do you think is the problem? And it provides me a way to like provide useful help instead of getting mired with one kid for the whole period. So.
I have 2 questions. One is, did you do this in CodePen, or like how did they run the program?
They have Macs, so I taught them how to like go. So I left this out. I have to teach them how to open up idle, which is like a Python development environment. It comes for free with TurboGrafx. They open up a file. When they submit their work to me, they use Google Forms. So they just like paste their code into a big old text box, and on Google Forms there's a way you can like edit your response. So you can go back to a response previously, so it's like a way of saving their work. You have to teach them that, and so there's whole assignments where all I'm teaching them, like I tell them I'm teaching them something, but it's really about can you get old work back from a Google form, or like are you saving it properly?
So they're not submitting their actual Python
No, they are.
topics to you. They do in addition to the Google form.
No, the Google form, they copy paste all the text
Right.
from their thing, and then they submit that in a Google form, so then I have this wonderful spreadsheet of every student's work.
But you're just seeing that you like never test their programs.
No, I do.
You do separately.
I run them all, and I...
So then they email you their...
There's a Google form
Yes.
that
and they,
records their username,
Uh-huh.
and there's a big blank box that says submit your program here. They copy paste
right.
whatever they were working on
Oh, you
locally.
copy and paste it back in to run it and
Yeah.
test it? Oh,
Yeah, no,
that's-
it's a really, I need a
Okay.
better system, and this is the first year as a hack.
Because I
It's
was
not.
like, okay.
A better way is go around on a clipboard when kids actually have met the requirements, you like check it off. But I was learning.
The other is like really how young would be the youngest you would attempt this?
So I did this with 9th graders, and we're the Academy for Software Engineering, but the thing that people I think like really like we're unscreened. There's no test to be in our school, and there is a little bit of self-selection bias, but not as much as you might think. So our kids are coming in usually like 40-50% on grade level for math, and then I think it's like 40-50% on grade level for English, somewhere in that range. So like we're not getting like this is not Stuyvesant or Bronx Science or something like that. So it depends on, I wouldn't say the age, it depends on sort of the academic skill set.
Level, yeah.
Yeah, I mean teaching, that's a good, hard question. I don't know, because people sometimes say like you can do this with 5th graders, you can do this whatever, but I feel like it depends on like who are the 5th graders, are they getting parental support at home, like how good are their problem solving abilities, like have they been successful in school in general, and age is a very poor proxy.
I
think it's more about like how much background they've had. I mean, I taught it in computer science and in math. Like I taught at a school where it was required for all 5th graders to take computer science for 2 double periods a week for a term, and so that's where we did like that, all that variables for like months, really like.
Yeah.
So at the end of 5th grade, so then when they like, so in 6 and 7, when you try to transition, they've all had like really strong foundation.
Yeah.
So I mean, I think the important part is they have to have gotten some foundation.
And the foundation that you gave was in Scratch or in something else?
Something pre-Scratch, Microworlds.
Micro-
But Microworlds is turtle graphics. Like what we did was all that
Yeah.
turtle graphics. So
I have 2 questions for you. Why did you choose Python?
Yeah, that's my
So my familiarity, so I'm familiar with it as one, in all honesty.
Say that again,
I'm
sorry.
familiar with it. So the
Okay.
languages that I have written code in, it's because I was an engineer by background, are like, so like .NET languages, so like C#, C++, C, Java, Python, JavaScript, and I think that might be it. Like like functional languages, but dear God, no. I've poked around at Ruby, but never written anything meaningful. So I chose Python. We have a CS consultant in our school. We think that's maybe where like the APCS and college curriculum might be
Right,
going
yeah.
a little bit. That's we're not sure. That's 1. 2, Python, the syntax is very gentle.
Yeah.
There's not like, when I teach Java, it's like, I literally, the ignore this stuff, like this stuff isn't important, only hone on this. There's so many things where I'm like, all right, the import, we're coming back to that. Ignore it for the time being, like public class, whatever, ignore that one. Like super, ignore that one. And so like the, what I feel like is really important is to remember, like, what are all the things that kids have to ignore? And that's not something they'll just, like, they have to actively ignore it. So, like, you're adding burden. And so I feel like with these, like, the only thing is import, and then the turtle thing is new for them, but other than that, it looks just like Scratch.
And my follow-up question is, if you're not familiar yourself with Python, what would you recommend for us to become more familiar with it?
Well, have you tried processing?
So processing is available in the sense of like, it's in Java, right? So,
Except it ignores everything you just said that you have to ignore.
oh yeah, wait, is it its own?
It's
I thought it was.
processing for Arduinos, like the using the.
Wait, it's not a language, right? It is Java.
It's Java.
Yeah. So I guess
It's not just for
the thing about that I've worked with processing. The one thing that and I don't know if this is my bias or not. There's like this draw loop, and I have to explain to kids like, okay, it's a loop, but it looks like this thing, but like it's really running multiple times. And like I've tried to bake into their heads the tracing part, like the computer does it, like that there's a secret behind the scenes loop going on. Not that that's.
But can't you do everything in setup then?
You can, but then it's like, why does it have to be in, like I was just trying to do the smallest transition away from scratch. If you look at a full TurboGrafx Python program, it's dead simple.
Okay, so then can you finish answering the question? How would you best suggest someone
Into Python? Like learn Python? We should talk. I can give you some resources for like this style of thing. There isn't a lot to know if that was all you were teaching. When you start getting into classes and methods, which this did not delve into, right? Like nowhere here did I talk about classes, methods, or functions. I forget what they're called in Python. Various other things. But there's a lot of resources. People here might be good. Okay, good.
There's a Coursera course in Python that starts in about 3 weeks. It's free.
Where is it?
Coursera, Coursera. It's online. Yeah, it's about an 8-week course. And I sometimes will have students take courses.
Yeah.
Code Academy is a
Code Academy has Python that might be a good familiar. Yeah. I don't have one because I feel like there's so many, especially for Python.
Yeah, I just typed in Python tutorial and there were like so many that come up.
Would you intend to go further with this? Like, do you want the kids to be able to transition to writing classes? Is that?
Oh yeah. So this is the end of our 9th grade curriculum. That year, the furthest we got was conditionals. And again, I hate saying conditionals because like you can nest the heck out of conditionals for very complex statements and like. So, with the forewarning that all the things when I say conditionals, it would be scoped to a certain type of context or a certain type of problem. But we did a little bit of conditionals, a little bit of variables, loops in Python, and we got to, the last thing we really did was like functions that take parameters. And that's like an interesting thing to do.
All in Python.
Yes. And then right now, the sophomore, they transition. Our school's still working out like the curriculum schedule based on teachers and it's a little bit complicated right now. Like we don't have our official, this is the best sequence. But we have a teacher who's into Bootstrap and Racket, and he's teaching with that. So this would be the year after. I teach in Java because we think we sort of have to prep for APCS for various requirements for our school.
Have you, and I don't know how it works because you teach at high school level.
Yeah.
Alignment for like, let's say Common Core or through, like for instance, middle school, because they don't test science anyways until 8th grade.
Yeah.
So the way my principal would test to see if our computer science course is working is problem solving.
Yeah.
And seeing if they're doing well in their math problem solving.
So if you were interested in a really tight and I don't have enough experience and I know like it's not gonna be Scratch.
Yeah.
Where's Rosanna? So there's someone here from Bootstrap. There's a curriculum and a tool, and it's for algebra, so I don't know if it's applicable to middle school math, but like there's this their goal is math CS overlap. Like they've thought really hard about it. And I'm not saying it's perfect but like I haven't taught it, but if you're just looking for things to pour ideas, like I would go with the people who have said this is our explicit goal, and I know they really try and target like the explicit goal is like all kids. It's not meant to be like, oh, here's an elective that some kids will take. So Bootstrap might be a good resource.
I don't know if you mentioned this before or if I missed it. So can you just kind of give me a sequence? So you teach Scratch for a set amount of weeks.
Yes.
Right, and then you move on to the transition to Python. Is that correct?
So at our school, I like rip these out. This isn't like they all got taught in this sequence. This was actually spread out. So like we did those 2 lessons in Scratch. We covered other topics in Scratch. We did a bunch of things. So our school, and again, this is not the best idea ever, but this is our logic. Teach them a bunch of Scratch with the goal being like, you can make things, and here's some core CS concepts. We transitioned to a unit we call the web. So we teach them HTML, CSS, and some basic concepts about how the internet works, and we feel like that's valuable from a programming context, because the web is a very gentle introduction to syntax. If you forget like a less than sign, it's not like the whole web page doesn't work. It just gets a little nice, you know, not so nicely formatted. And then we do a unit called data, where we've been looking for tools, but what I settled on was spreadsheets. I felt depressed at first, but then there's interesting things you can do with them. So literally just getting kids to, one of the things that we feel like, not that Scratch doesn't do well, but isn't a focus, is getting computers to answer questions for which you don't know the answer ahead of time. Like when you design a video game, you sort of know what should happen, or when you make a story, you know what should happen, but how do we get computers to answer questions for which we don't know the answer ahead of time? So like, I had an assignment in spreadsheets where they use functions, and relatively simple ones, to like make a radio station, or like an online streaming radio station to get the most listeners. So I have like some secret function hidden behind that's like, as they conform to the total amount, like they get a big data set of all the downloaded music that's ever been downloaded in the last couple of years. And if they can map the genres proportionately to the, and I don't tell them they need to do that, like they can tweak the numbers and poke. And then after they do that, we go into Python. So like, we sort of take a detour into other things that will prove useful later to give them sort of a break from just all this programming. Sorry, that was a long answer, but the lesson 0 and lesson 1 were separated from this stuff by like 4 months.
Okay, so that whole sequence that you just mentioned is a year-long course?
Yeah, it's a year-long course.
And you said before it was 60 minutes once a day, is that correct?
So this will vary as the school changes. These aren't like set in stone, but they saw me 3 times a week for 2 periods for 60 minutes and 1 period for 75 minutes. So about 3 hours a week.
3 hours a week.
Yeah.
Okay, and is it, what do you call this course?
Introduction to Computer Science.
Okay.
Because, I don't know, the name doesn't matter. So I'm in a school, all the kids have to take it. So there's
they
not,
all have to take it.
yeah, like every 9th grader takes intro to CS.
Okay. May I ask the type of students, or as far as their backgrounds, are they?
So we're probably representative of like median New York City public schools. The metric I said, I don't know for recent years, but our first year class, I think it was like around 40-50%, or maybe slightly higher than 50% on grade level for math. And then I know it's sub 50% on grade level for English.
Do you know how many girls versus boys?
Oh, we are dramatically overstacked for boys because we suffer from the, so I did work for Girls Who Code over the last 2 summers. It's the whole, like by the time girls are even applying to high schools, it's already been sort of culturally messaged to them in a lot of ways that like, this isn't for you, or, you know, CS is just like dudes in basements. So we are probably like 80% male. And so our school right now, we can't, since we're unscreened, we don't choose, like it's a lottery system and kids who rank us. So we're right now doing a lot of work to partner with certain middle schools to be like, no, this is for girls. Like you're sending us good ones who are successful here. Like, can we get like a pipeline going? Because like we need to get that number up.
I was just going to say, for younger learners, or to mix it up, a lot of these can be translated into physical activities.
Oh yeah.
Which I think is really fun.
No, that's why like Turtle. So I'm teaching like an APCS light curriculum where I use like all these things where it's all about like movement and like it explicitly makes the idea that the computer does this and then this and then this and then this and then this, which again I feel like kids are naturally weak on. Like it brings it out. Like when you run the program, you watch the thing happen in sequence. So I, as much as they're like old school, I feel like they're really valuable. When you get like more complex programs and the computer's like doing all these things that seem like they're happening at the same time, eliciting the sequence is harder. We should probably wrap up soon, actually.
Do your kids take the AP Computer Science? If so, what year?
So we ran some sophomores at it this past year. Our pass rate was not as high as we would like, and the conclusion I drew from that is their brains are fine, their habits are very weak. Like literally, I'm teaching a CS class where I don't call it this, but in my mind it's 50% habits and 50% CS. So like they don't study. By now, like most of our kids don't come in studying, or even knowing how to study. Like they think like looking at your notes is studying, as opposed to like let me solve a practice problem. Or they come in like trying to think what, just like classroom expectations of how much they should know and retain. That like if we talked about it in class, you should know it for the next
Do you
class.
give homework for this sequence of courses you just explained?
For intro, or for intro, we are very much aware that not every kid has access to a computer at home. So there's never like, especially in 9th grade, there's very little explicit homework. What it tends up being is I just try to design assignments that are differentiated
Well,
in
like
terms of.
that handout that you showed,
Yeah.
where they put in the angle at one,
Yes.
and then like that's the reason why I've done pseudocode for homework, is because
Yeah, it makes them
like,
think
it
about it.
doesn't require a computer at home.
Yes.
Like you can write on paper.
Yes. So 9th grade, we could, I don't know. Sorry, I didn't ultimately because what I saw last year is not like don't give them to them, they won't do it, but like think carefully about it. Because if like a bunch of kids don't do it, and everyone still does fine in the class, you're sending this message that homework isn't important.
Right.
So I want to be really thoughtful about giving it, and given all the curriculum design, I wasn't able to be as thoughtful as I was like in a way to like reinforce, like not sinking kids who aren't used to doing homework, but also giving them practice time. So that's a larger school question.
And
I
also
guess.
not reinforcing bad habits, or it could be.
Yeah. So what I tended to do was, if you wanted like a high B or an A, there were assignments that would require outside work, because like then there's this strong correlation. But there are kids who come in like, I haven't figured out how you get kids who have a history of never doing homework for like the first 8 years of school into doing homework consistently and not failing them, because failing them in 9th grade is like just is gonna screw them over for the rest of their life. So it's a hard problem, I find.
I just want to point out, as someone who's familiar with Python, is that when you look at solutions to problems, a lot of times the answer will be like a one-line solution, and it's very elegant, and it can be a little discouraging at times. But the normal expectations, I think, from beginners is that they're going to write lengthy code, and it's okay if it doesn't work, or if it's not as elegant a solution as like the one-liner. The other thing I want to also introduce is the Meteor JS platform, which because it's JavaScript throughout, it might give some kids, I think the older kids, some experience from developing something from the front end all the way to the back end, actually deploying it very simply. And so
that's actually the question I was thinking, is because you said you did the HTML, CSS. Like, do you ever go to JS?
No, so the reason I've avoided JavaScript is nice because web pages run on it, but like, and this is my intuition, I could be wrong. I feel like a lot of JavaScript, I taught it to girls who code, it's like, you do this in JavaScript because you do it. Like on-click is this way because when you want to be clicked on, it's this way. Like JavaScript uses a lot of high order functions, right? And like, and this might just be my personal teaching style. Like I have this strong aversion, like, oh, you just do this. Like just do it because that's the way it works. And not that they need to know like every level of depth, but to do some of the richer JavaScript projects that I've seen, it might just be that I've been exposed to the wrong ones, require kids to like when they're like, why doesn't this work? It turns into me telling them the line of code to write, not like an informed discussion of like why it doesn't work. But that's just that's opinion. Like that's not research.